Hello, everyone, and thanks for joining this talk on exploring the wonderful world of Python on devices. My name is Brandon Tatram, and I'm the VP of Developer Experience at Blues Wireless, an IoT product and services company that's transforming the way developers build connected solutions. Now, today, I want to talk about Python and give you my perspective on why I think Python is such a powerful language and why it matters in the world of embedded development. I'll start with a bit of history, talk about some of the flavors of Python available on devices, and mix in a few demos as we go along. But first, let me start by stating why I think Python matters at an embedded development event in the first place. Now, I could start by criticizing the C and C++ languages or making some joke at their expense, but I'm not going to do that. I will say, however, that C and C++ aren't for everyone, and the learning curve for these languages is quite steep, as I'm sure many of you well know. And when it comes to considering programming languages in embedded systems, we should consider that businesses around the world will deploy billions of more embedded and connected devices in the coming years. And those devices need developers, many more developers than those working professionally with C and C++ today. So the question becomes, what are our options as an industry if we want to enable the next 50 billion embedded devices? Insist that C and C++ is the only path through the door, or consider it another approach. Now, of course, you may point out to me that according to the TIOBE index for August of 2021, C is still the most popular language, with C++ coming in at number 4. And you'd be right, though Python did move solidly into the number 2 slot over the course of the last year. There is no doubt that C is still popular in terms of what people are using for current apps, what they're maintaining, what they're actively working on day in, day out. But what if we looked at the data a different way? Specifically, not what people are actively using, but what they're learning and hope to use in the future. Because isn't that the best indicator of where the long-term opportunity lies? And here, the data are pretty clear. Based on an analysis of people searching for language tutorials, Python is the clear favorite. It's the favorite among people that aren't just using a programming language day in and day out, but learning something new for the purposes of building a career in a space, using a language for their next project, what have you. It is where the most greenfield opportunity lies. And Python is already a language that can and is being used in a number of areas, from web development to machine learning, data visualization, game development, and more. It's also becoming the most popular programming language for introducing coding to students new to programming, from kids to adults. It's the language that people are learning from the age of 8 to the age of 18, 28, and beyond. This is the language that people are focusing on by and large. So if we're looking to pin down the next generation of IoT devices, how they will be built and what they will run, I think you can look no further than Python. So before I get into the specifics of working with Python on devices, I thought it might be helpful to share a few of the advantages of Python on devices, at least as I see it. And it starts with compilation. Now, those of you that are embedded engineers are very well aware of the compilation step in taking anything from our local development environment and building a binary, you put it on a device. And with Python, you don't have that. Again, as an interpreted language, it runs as an interpreted language, even on a microcontroller or on a single board computer. So you have the option of the very quick code, try, fail, and repeat loop that you get in any kind of an interpreted language. And it's not one that gives you a performance tax for being interpreted. As our microcontrollers, as our single board computers get beefier, heavier, more powerful, memory efficient, what have you, it's easier and easier to use an interpreted environment on those devices. The second is live debugging, and this is one of my absolute favorites. You'll see this when I give you a demo in a few minutes of this. But being able to actually open a REPL on a microcontroller, on a single board computer, and actually inspect the device, its available pins, the state of its peripherals, all those kinds of things, is a very powerful construct, and it's one that I use all the time, that live debugging capability, without the need for a programmer, without the need for an extra link device. That's actually really nice. And then next, machine learning on single board computers. This is an especially important thing with the Raspberry Pi class devices and beyond. This ability to be able to actually run inferencing live on machine learning against machine learning models with video, with images, with a microphone, with an IMU, what have you, is a really powerful construct, and Python really unlocks a lot of that capability. And then finally, And I will admit I'm biased. It's Python. Python is a fun programming language. It's easy to get into. It's very powerful, and it is absolutely fun to use. And so, again, biased, but I consider the language itself to be one of the powerful reasons to consider using it. So now let's talk a bit about Python variants and when you'd want to consider each for an application. The first is CPython, or the original Python. This is the Python that was built for desktop environments. This is also the Python that runs on most single board computers that you're working with. Because most SBCs run a distribution of Linux, that's the version of Python that you're going to end up using for most of these applications. And this is great for applications on a Raspberry Pi or another SBC like a Jetson Nano, Google Coral, or what have you. Now, the one caveat to be aware of is that Python 2.7 is still the default distribution on some Linux distributions. So you will want to make sure that you're running Python 3 as you're working with any of these. So let's actually look at a demo. For the first demo today, I'm going to actually walk you through using Python on a Raspberry Pi. So let's switch over and do that. So for this first demo, I've got a couple of devices here on my desk. There's a Raspberry Pi 4 configured, ready to go. And on this breadboard connected to the Pi is an Adafruit BME 680 temperature, humidity, pressure, and gas sensor. And I'm going to, with this first demo, actually show you how you can talk to that device with Python on the Raspberry Pi 4. Okay, so I've already SSH'd into my Pi, and I'm going to CD into my ARM demo directory. And then I'm actually going to use the virtual environment feature of Python 3 to activate an environment that has just my local dependencies installed. So if you've ever used a package like NPM, this is very similar to being able to just sort of manage your dependencies in one simple area. Ruby has a very similar construct. And so I'm going to do source env/bin/activate. This will load my virtual environment, and then I'm going to show you my main.python file. Pretty simple. My only real dependency here is the Adafruit BME 680 library, which I have already installed. And what I'm doing here is I am using the Adafruit bus.io library to open an I2C connection on my default SCL and SDA pins on the Raspberry Pi, which I have the BME wired up to. Starting an instance of the BME 680 device over I2C. And then I just have a while loop that does most of the work here. I'm getting the temperature and humidity, and then I'm printing those out to the console and then sleeping for 15 seconds. A very simple program, but this is effectively the way that it works in Python. If you're familiar with the Arduino side of the world, everything that comes before your while loop is your setup. Everything that shows up in a while true is effectively your loop. If you're from the C world, this is effectively the difference between main and running off of a system tick or something along those lines. So pretty similar construct, but again, all based in Python. So let me exit out of this, and I'm going to run python main.py, and you'll see the application in action. So it's reading from my sensor. It is 30.2 degrees Celsius in my office with 59% humidity right now. So pretty simple. This will keep running every 15 seconds or so. I'm not setting it anywhere yet. I'll show that demo in a few minutes, but that's just to give you an idea of how simple it is to use the Pi with sensors, with devices on a Raspberry Pi. Excuse me, Python with sensors with devices on a Raspberry Pi. Next is MicroPython. And MicroPython is a Python 3 implementation that was built and optimized for running on microcontrollers. This was the very first variant of Python that gained popularity to run on embedded systems. It has great support for the ESP32 and the recently released Raspberry Pi Pico. So if you're working with either of those microcontrollers, it's got great support, great docs, and is easy to get started with. So now for the next demo, let me actually show you MicroPython running on a Raspberry Pi Pico. So for this demo, I have a different Raspberry Pi device on my benchtop. This is the Raspberry Pi Pico, which is Raspberry Pi's latest microcontroller featuring the RP2040 chip that they designed themselves. This is a MicroPython device. It is a microcontroller, so not a single board computer like the Big Brother Raspberry Pi. And this is also connected to an Adafruit BME 680 temperature, humidity, pressure, and gas sensor over the breadboard on the device. So let's take a look at what MicroPython looks on this device. Okay, so I've opened up Visual Studio Code and I am running a MicroPython extension here that actually allows me to interact directly with my Pico. But you'll notice from the source code here that this is actually very similar to what I just showed you on the Pi in the last demo. There's a few differences in terms of the pin management and I2C-bus through the machine library, UTime slightly different than time, but I'm using a very similar implementation of the Adafruit BME 680 library. And a few differences here is this time I'm actually assigning an LED pin. There's an LED pin on the Pico that I'm going to interact with, but I'm initializing the sensor just as before, reading the temperature and humidity, sending that out to the console so that you can see it. But I'm also toggling the built-in LED off and on while I'm taking readings and then going to sleep for 15 seconds. So using the extension, what I'll actually do now is run that on the device. And then that'll take a few moments. And once that shows up on the device, it'll actually open up a terminal and a REPL right in Visual Studio Code itself. Great, so that's connected, and this gives me an opportunity to show you one of my favorite features here in using MicroPython and CircuitPython, and that is this REPL to be able to actually inspect and work with my running devices through the interpreter, which is really powerful. I'm basically inside of a Python REPL right now, so I can do things like call Python commands before, like from machine import pin to actually pull in the pin library. And then I can use the dir command to inspect the functions, attributes, properties on that device. So I can see that the pin library gives me in, IRQ, falling, rising, out, pull down, pull up, all that good stuff. I can actually toggle pins using some of these built-in functions. And then again, I can do all of that with the interpreter. I can also do things like pull in the Python standard OS module and then do something like print os.uname, which gives me information about the actual microcontroller that I'm running on. So I can see that I'm on the RP2. This is the Raspberry Pi Pico with the RP2040. You can see the version, extra information about the version as well. And that's really powerful. But I can not only actually interact with the device and inspect pins and see libraries, but I can actually do things to control the device from within the REPL. So I'm going to assign the pin 25, which is the built-in LED on the Pico, and assign that to a variable called LED pin. I'm going to create a new instance of the LED object with the pin mapping, assign LED pin, and set that using the pin module as an output. And then I can actually use, if I look at dir LED now at this point, it actually will show me the things that I can do. So I can set the value, I can initialize it, set it high, low, etc. In this case, what I'm going to do is I'm going to say LED.value. And if you look at the hover of the demo here on the screen, you'll see that actually turns the LED on the device. And again, I did that from Python, from the interpreter on my device. I can then do LED value 0 to turn it back off. So again, this is the REPL on my device, but I'm not actually running my main program. So in order to do that, which I showed you earlier, I can hit Control D. That does a soft reboot, and now my main application is running. I'm pulling in the temperature and humidity from that BME 680. You'll see it's 29.9 degrees Celsius and 61.4% humidity. And that again we'll sleep for 15 seconds before running again. Next up is CircuitPython. Now, and this is a fork of MicroPython, but it was focused on adding some more CPython compatibility and really ease of use for early programmers or folks that were new to the embedded world. It's actively supported and developed by Adafruit, as well as a large audience or a large community of contributors. And it has great built-in board support for Nordic, STM, and SAMD microcontrollers. So there's a lot of different MCUs out there. If you buy a Feather compatible device from Adafruit, chances are it has support for CircuitPython right out of the box and some great resources for using. So I'm actually going to show you a demo of CircuitPython, but I'm going to do it with a brand new device that Blues Wireless, my company, just released last month called the Swan. It's an STM32 MCU that has support for Arduino, C, C++, and CircuitPython, and I'm going to show it to you in the context of CircuitPython today. Now for this next demo, and actually the last demo as well, I'm going to use the setup that you see here on the desk before you. This is the Blues Wireless Swan, which is an STM32 microcontroller that runs CircuitPython. There's the same old BME 680 on the desk there, and there's also a board sitting here called the Blues Wireless Note Carrier that has a note card, which is a device that I'll tell you about before the next demo, but that's the setup that we've got for this next piece. Now, you'll notice here that this is a different IDE. This is an editor called Mu. The actual code is almost identical to what you saw in MicroPython. I'm using very similar constructs, are slightly different, time instead of U-time. I'm using the same Adafruit library, have the same while loop, grabbing temperature, humidity, and printing that out to the console. I have the same capability to use the REPL here as I do using in MicroPython, but here I figured since I've shown you that already, I'll just show you in CircuitPython the same demo from before. Temperature 30.29 degrees Celsius, humidity 61%. And again, that sleeps every 15 seconds and repeats and does the same thing again. So pretty simple, very similar, only syntactically different on the CircuitPython side from MicroPython. Now, before I wrap things up today, I do want to spend a moment talking about the Internet of Things. And I recognize that not every embedded application is a connected application, but more and more of the devices that we are building do rely on some kind of internet connectivity. And there's good news for the Python world here as well, is that there's an increasing number of IoT vendors out there who are building for the Python developers, not just the mainline C and C++ embedded programmers out there. One such example is my company, Blues Wireless, and we provide a device agnostic way of connecting your sensors and applications to the cloud using a product of ours called the Note Card, which is a cellular device to cloud data pump. So the Note Card can work with any host. It works with any programming language from C, C++, Arduino, Python as well, Go, any of those languages that you can work with, you can actually work with the Note Card and pump your sensor data into the cloud. And not only that, but we're not just device agnostic. We don't just tell you, yes, you can use this device with Python, but we actually actively support the Python developer experience through our CircuitPython support on the Swan, which I just showed you, as well as a complete SDK for our Note Card product that works out of the box with CPython, MicroPython, and CircuitPython, all from the same library. So if you're working with any of the devices that I just showed you, whether it's a Raspberry Pi or whether it's a MicroPython device with a Pico, or a CircuitPython device with a Swan, or a SAMD51, or NRF class device, any of those will work with this exact same library to talk to the Note Card and actually send data up to your cloud applications. And it's a really powerful construct. We want to make it as easy as possible for developers to get started with this device. And so that's going to be my last demo. I'm actually going to show you very briefly what it's like to actually take an existing Python application and add some more Note Card style compatibility or flavor to it. So for the final demo here, I'm going to take the exact same CircuitPython example from before, again using the Swan, and I'm going to add the Note Card to it. That was the device that you saw in the image a few minutes ago, right there, connected in through the Feather Swan device. Note Card is a cellular data pump. It speaks 100% JSON, and the Note Card SDK allows me to send very simple commands to the device. And so I'm going to actually configure its connection to the NoteHub Cloud service on the other end. I will read the temperature, humidity like before, but this time I'm also going to add that data to the Note Card through this note.add, again, JSON command. It'll add that to the device, and then again, sleep as before. But now when I actually save this, what I'll see is some additional information on the console. I'm seeing notes as they're being added to the device. The Note Card is letting me know it's there, and it is actually in the process of syncing that up to the cloud service as we speak. Again, 100% Python, very easy to use and very easy to work with. Now, the cloud service side of the Note Card is NoteHub.io, and every Note Card is securely connected to the NoteHub through our cellular network and connections to securely send its data into this cloud service so that you can then securely send it out to your own cloud applications of choice. And just by those few lines of Python code and sending data to the device, I'm able to actually see events showing up in the device. These are all actually showing up right here. Humidity 61%, temperature 39, and those are showing up every 15 seconds or so. From here, I can route that out to whatever cloud application I prefer, whether it's a DataCake or RubyDots or even AWS, Azure, etc. And that's it. So hopefully you enjoyed those demos today. And as I close, I want to give you a couple of resources that you can look to for getting started with Python on devices. So circuitpython.org is always a great place to get started to learn not just how to use CircuitPython, but to explore all of the varying devices that are available with that language. Micropython.org as well. The Raspberry Pi Foundation has great docs for using MicroPython on their Pico, as well as their silicon, their RP2040, which is the core chip on the device. And then finally, if you are interested in exploring the Note card and adding cellular IoT to your Python-based project, dev.blues.io is the place to get started. And we actually have resources and tutorials for building a new application that controls the Note card from Python. So thank you so much for taking the time to listen today. I hope you enjoyed it. You can reach me at bsatram@blues.com or find me on Twitter as Brandon Satram. Happy to answer any questions that you all have through the course of the rest of the session today. And enjoy the rest of the show. Thanks very much.